Video, I am going to work through some exponential and logarithmic applications. In this first problem, we have world population growth. World population in millions closely fits the exponential function f of x equals 6084 times e to the 0.0120x, where x is the number of years since 2000. The world population was about 6,853 million in 2010. How closely does the function approximate this value? Well, x represents the number of years since 2000, so in 2010, x would equal 10. So we're simply going to take 10 and plug it into this function. I will show you how to do that using Excel. So to do a computation in Excel, you start with typing in equals. We have 6084, and we're going to multiply that by e to a power. So times is shift 8, the asterisk, and to get e as a base, in Excel you use the formula exp. And then inside this formula will be the actual exponent. So 0.0120 times x, which is 10 in this problem, and close the parentheses. So in Excel, equals 6084 times exponential, or e to the power, 0.0120 times 10, which gives us 6859.691 million. I am going to round this down. I go to Home, and here where it says number, we got the round down button. Just take it down. I'm going to take it to the whole million. 6860 million. And it's off by 7 million, but as far as significant figures, I think that's pretty good. Now in Excel, if you want to see how you computed what's in the cell, when you click on the cell, you can see up what you typed up here in this input bar. Also, if you double click on the cell, you can see what you've written. All right, so you can double click in here to see what is actually typed in the cell and how to compute it. Now let's use this model to predict world population in 2020 and 2030. Well, in 2020, that's 20 years after 2000, so x equals 20. And in 2030, that's 30 years after 2000, so x equals 30. So let's see, we're going to do x equals 20, and now I'm simply going to do this compute this function again, but with x equals 20. So 6084 times exponential, which is e to the power of 0.0120 times 20 this time. And we get 7,734 million. Then for 2030, where x equals 30, we get equals 6084 times exponential for e to the power of 0.0120 times 30 this time. We get 8720 million. Let's take a closer look at this function. It's exponential, so we know that it is growing at a greater, ever-increasing rate. So you know the graph will look something like this here, where 6084 is where it crosses right here. It's actually the starting point. So we really don't need this part down here. We really just need this part here because the smallest x can be is 0, which is at year 2000, and at 0 we have y, or the function f of x, equal to 6084. So this 6084 is the y-intercept, or the starting point at x equals 0, and it's increasing at an ever greater rate as the time goes on. That's the definition of exponential growth. Let's go ahead and look at the next example. Employee training. All right, there we go, fix that. A person learning certain skills involving repetition tends to learn quickly at first. Then learning tapers off and skill acquisition approaches some upper limit. Suppose the number of symbols per minute that a person using a keyboard can type is given by the function f of t, where t is a number of months the operator's been training, equals 250 minus 120 times 2.8 to the negative 0.5 t. So this is an exponential function because we have an exponent here, but we have a negative power and then this 250 in front. So what is going to happen with this? We will graph this function, but first let's go ahead and evaluate it for certain values. So remember, t is the number of months the operator has been training. So after 2 months, the number of symbols per minute will be found by 250 times, minus 120 times 2.8. Shift 6 to get the caret, that gives us our power. Put it in parentheses if there's going to be an operation also in the exponent, which there is because we are taking our negative 0.5 and multiplying it by 2 months. So after 2 months of practice, the operator can type 207 symbols per minute. What about 4 months practice? Equals 250 minus 120 times 2.8, shift 6 to get to the power, open parenthesis, negative 0.5 times 4 months this time, and we get 235 symbols per minute. What about 10 months? Equals 250 minus 120 times 2.8 to the power, open parenthesis, negative 0.5 times 10 months this time, 249. Notice this 249 is nearly 250. So what is this 250 here in the equation? Well, let's graph this using Excel. I'm going to copy the formula and do the graph on a separate sheet. So here, notice I click this plus to get a new sheet. Double click down here to name it. I'll name this graph 2 because it's graph for problem 2. I copied the formula so I could see it when I type input that I will use to make the graph. So we're going to need values of t and values of f of t. Let's go ahead and start at 0. And we'll increase by 1 until, let's say, 15. So 1, 2, 3. I'm going to just copy this pattern now by highlighting, pointing my cursor to the bottom right where there was that green square. Then I'm going to left click, hold, and drag. I went to 19. Let's go back to 15. I don't think we'll need those extra ones. And now I'm going to type in the formula to find f of t, so I don't have to do this 16 times. So equals 250 minus 120 times 2.8 to the power, open parenthesis, negative 0.5 times, and this value of t is going to change, so I'm just going to click on that first value of t, which is in cell A4, close the parenthesis, and hit enter. Now, this, notice, is actually the y-intercept on the graph. This is where it starts. I'm going to put the cursor on the bottom right corner where that little green square is till it becomes a little black plus. Left click and drag the formula all the way down. So notice here it changed from A to A15, right? We started up here at A4, and as we move our way down, Excel automatically changes it. So this is a nice way to save time using Excel and the formulas. Also notice down here, remember we had 249 when we did 10 months, but notice if we keep adding decimals, it stays at 249, but it keeps getting closer and closer to 250. Here at 15, we're at 249.95. Right, so it's getting closer and closer to that 250. So it looks like that 250 is an upper limit. Like the maximum number of symbols per minute this operator would be able to do, to type, is 250, despite any additional practice after basically 15 months. So to graph this now, I am going to highlight all the data. I go to Insert, and I'm actually going to this graph of the scatter plot, but instead of graphing points, I'm going to have them connected by a curve. And here we go. And notice this actually doesn't look like our typical exponential function. It in fact looks more like a logarithm, but it's not a logarithm, as you can see. So this type of function, where there's that 250, notice that's our upper bound right there, doesn't get beyond the 250. So 250 is the upper bound. Okay, so we can see that right here. So this 250, which is also here in the formula, that is an upper bound. The 130 we saw right here, it's right here. We saw that was the time at t equals 0, or how many symbols the operator could type when starting the training. Okay, that says 130 right here. We see it increases and then flattens. What we might not be able to see is a curvature change. It starts to increase in a concave up pattern like your typical exponential, and then it changes to a concave down pattern. And this kind of graph and function is called a logistic function. Starts off as exponential, but it doesn't increase forever, but it flattens out at some upper limit. That is a logistic function, and this is one form of a logistic function, your maximum minus number times base to a negative exponent. Let's see if we can blow this up a little bit and see if there is a curvature change. We may or may not be able to see it. So let's first clear all this writing. And see if we can make this part bigger. So really I want to see what's going on here. And that's just in the first 2 months. Because then we can see it's definitely concave down at this point, but it's probably concave up right in the beginning. To do that, we are going to have to make another graph, but with the inputs be much closer together, say separated by tenths. So let's try that. So let's do another graph down here where we have t and f of t. We'll start at 0, but now we will go to 0.1, and I'm going to write a formula. Click on the previous and add 0.1. That's the formula I'm going to use here, and I'm going to copy that all the way until we get 2. This went to 2.8. We don't need to go that far. Let's see if that is enough for us to see the curvature. So we need to write the formula again. 250 minus 120 times 2.8 to the power, parenthesis, negative 0.5 times t. And let's copy this like before. And let's graph it and see if we can kind of zoom in on what's going on between 0 and 2. So we're going to insert that same scatter plot but connected by lines. And now, doesn't really look like there's much of a concave up part. It looks pretty much like it's all concave down. You'll see that in many logistic functions, it will actually start as a concave up. It'll do something more like, I'll exaggerate on here, but it might do something more like this and then start going down, see? And that's what I mean by starting concave up and then slowly heading towards the upper limit. So this here, this little part of the exponential, doesn't look like it's really happening on this one. And if it is, it's so minor we can't even see it. Okay, so that was our second exponential, and which was actually a logistic function. Let's go back to the applications and move on to our third example, which is now logarithmic. And remember, natural log, ln is natural log and it's base e. The number of leisure trips within the United States in millions of person trips of 50 or more miles one way over the years 2009 to 2014 can be modeled by the function f of t equals 1458 plus 95.42 times the natural log of t. T has to be at least 1. Okay, so t represents the number of years since 2008. F of t is the number of person trips in millions. And we want to use the function to approximate the number of person trips in 2012 to the nearest million. And then compare it to the actual number of 1588 million. So in 2012, that is 4 years after 2008. So for this example or this problem, t equals 4. So let's type in our function equals 1458 plus 95.42 times ln, and notice there's a function in Excel, ln, where now we just type the argument, which here is represented by t, and we're doing it for t equals 4, 1590 million. The actual value was 1588 million. Again, that's a pretty good approximation. Let's now look at the graph and discuss its properties. So I'm going to create, well, let me first copy this, Control C. Then I'm going to make another tab. We'll put graph problem 3 here, enter. Make this a little bigger. Let us paste the function so I can see it. And remember, t started at 1. Then we have f of t. And we want to do then increments. Let me look back and see. So t greater than 1, then the number of years since 2008. We are in 2020. Let's try doing 12. Let's go by 1 year and do 12 of these and see if that will be enough to give us a graph. So we'll just do 1, 2, 3. Now I'll just copy this pattern down to 12. Whoop. There we go. We'll write the formula equals 1458 plus 95.42 times natural log, then I double click and then click on our input for t, which is the argument of the natural log. And as I copy this, this cell will change A4 to A5, 6, 7, 8 all the way down. Copy by pointing to the bottom right, left click and drag. Right. Let's now copy these. We will insert, scatter, but connected with just the line. Here we are. So we can see here at t equals 0, I'm going to put the graph here where we can see it. At t equals 0, it's 1458. So not 0, 1. So right here is where t equals 1. And so this point over here is the 1458. All right. And then we see this concave down shape again as it increases And it looks like it's getting close to 1700, but unlike the logistic function where it will actually flatten out, this won't flatten out. It'll keep increasing forever, but at a much slower and slower rate as time goes on. As you can see, it starts going up fast and then it gets flatter, flatter. It will never get completely flat, though it might look that way to our eyes. Let's see what happens if we do add some more values to this. So let's see if it will let us bring this down. Well, first I need to have numbers in there, don't I? So let's go ahead and continue this pattern. Whoops, did not work. 10, 11, 12. Let's just do this equals this plus 1. Might as well go to 30 since we're so close. Oops, too much. Let's just go to 30. And then I will extend the formula. Okay. What we can do is I'll click on here, go to Design, select Data. And now I want to edit my input here. Okay, we want X to start at A4. Wonder why it says A5. I might have missed something here too. Huh, I did miss something there, right? This time. So let's go ahead and change this. So I'm going to go from 1 down. I'll change this. So I want this to go from this 1458 all the way down. Okay. See what happens. Okay, going so far. Now, it's not as easy to see as the other one because we've kind of we have a larger range now. And so we can see before we only went up to around here. But we see as we extend, it does keep increasing and it will continue to do so. And so that's what the logarithmic function looks like. When t equals 1, by the way, natural log of 1 or any log of 1 for any base is 0. So that's why we started at 1458. So when you're starting with a logarithmic function at t equals 0, t equals 1, so that natural log of 1 is 0, this number out here, okay, that's your starting point as we saw earlier, 1458 would be around there. All right, let's move on now to the next example. And here we see another function with e to a negative. So this is another logistic function. We have another logistic function. Notice when t is 0, e to the 0 is 1, and 1 minus 1 is 0. So this would start at 0 because he's starting at rest. What am I talking about? Well, at the World Championship races held at Rome's Olympic Stadium in 1987, American sprinter Carl Lewis ran the 100-meter race in 9.86 seconds. So see, when he's starting the race at time t equals 0, he's at rest. His speed in meters per second after t seconds, so t seconds, is closely modeled by this function here, 11.65 parentheses 1 minus e to the negative t divided by 1.27 this time. So how fast to the nearest hundredth was he running when he crossed the finish line? Well, we're told he crossed the finish line in 9.86 seconds, so t will be 9.86, and we can figure out his speed. So right here, I will remind us that t is 9.86 seconds. And then here we'll write the formula equals 11.65 times parenthesis, 1 minus, remember e is exponential, so exponential, this is like e to the power of negative t, and our t is 9.86, divided by 1.27, close the parenthesis. Right, now this second set of parentheses is for this exponent. To close this parenthesis, I need another one, so double close there. 11.64 meters per second. We want to the nearest hundredth. We will round that down, again by going to home, number, taking it down, whoops, too many, 11.65 meters per second. All right, next question. After how many seconds? Oh, this time we need to find t. Remember here, t is in the exponent, so we're going to have to solve for this exponent. After how many seconds to the nearest hundredth was he running at the rate of 10 meters per second? Notice when he finished, he was at 11.65 meters per second. So somewhere along the line, he was running at 10 meters per second. So that means f of t equals 10. So I'll just write that here. So what we're doing now is we're given f of t equals 10, and we want to find t. So I'm going to put a 10 here. Then over here, I'm going to type a space before an equals because I'm just going to be copying down the formula and not actually doing a computation yet. So 11 point, this was like what you would do on paper. 11.65 parenthesis 1 minus e to the power negative t divided by 1.27, close the parenthesis. Oh, but I really should have parentheses around my exponent as well. So there's another set of parentheses around the exponent. So this is what we need to solve. Something like this, when you have this coefficient, let's divide out the coefficient. We're trying to solve for t, which means we ultimately want to get the e to the power part isolated, right? This part here we want by itself. So we have to get rid of the 11.65 and this 1. So let's divide this 10. Notice I can actually just click on the 10, divided by 11.65. Click in here, space, equals, and I'm just going to copy, Control-C, Control-V, what we have left. So notice what I did here was we want to divide by 11.65. So the left side now is 0.858369. We're trying to get e by itself, so let's subtract this 1. So next, subtract 1. So equals this minus 1. Notice it's negative now. Space equals, and we just want this exponential part. Control-C, Control-V. All right. Oops, I forgot the minus there. Both of these are negative, so let's divide out the negative. So equals, I'm just going to put a minus this, because then it'll just make it positive. Space equals, and now we got rid of the negative, which I didn't have before. All right, so we have e to a power. We want to get to this value in the power. So how do we do that? We use the inverse of the exponential, which is a logarithm. And since this is an exponential base e, we're going to take the natural log of both sides. So what I did to get here was I divided by a negative 1. And now I'm going to take the natural log of both sides. So equals ln, and here it is, I'll double click, want the natural log of this, equals, Now here, when I take the natural log of e, I'll go ahead and type this in. ln of, should still be there, yeah. Remember, so since these are inverse functions, the natural log and the e cancel each other out. So what I am left with is just the -2 divided by 1.27. So let's go over here. Equals this. I've just put that back. And then on the other side, I have equals. Natural log and e canceled out. So I have -t divided by 1.27. I want to get rid of the negative and the 1.27, so I'm going to multiply both sides by a -1.27. So multiply by -1.27, scoot this over, equals this, times -1.27, space, equals, and now we have left is t. So to the nearest hundredth, it took 2.48 seconds for Carl Lewis to hit the 10 meters per second rate. Well, now let's go ahead and look at this function. I told you it's another logistic function, so you should have an idea how it starts increasing then flattens out. So Control C. And I think I told you already that when t is 0, e to the 0 is 1, 1 minus 1 is 0. Okay, so we start at 0. But as t gets really, really big, since it's negative, this is like 1 over e to a really big power. Basically, this thing is approaching like 0. This is approaching 0. So we'll see that 11.65, this is going to be our upper bound. So let's create another tab for graph 4. Enter. Make this a little bigger. It's our function. T f of t. We finished in like 9.86 seconds. So starting at 0, we only want to go to 10. Well, let's see what happens if we only increment by units here. $11.65 times, open parenthesis, let's make this a little bigger, I'll have to do it in a minute, 1 minus e to the power, so double click on the exponential, negative power divided by 1.27, close, close. Okay, let me make this a little bigger, not that big. Copy this down. Let's see what it looks like. Insert. Yeah, this actually works quite nicely. There we go. Starting at 0, accelerates very rapidly. Again, and then flattens out. And notice it's not up to 12 because this is that 11.65 here. Right, so if you look down here, right, by 10 seconds we've reached the 11.65. Right, So another logistic function increases rapidly and then flattens off to an upper bound. So according to this model, he would not run faster than 11.65 meters per second. All right, very good. I believe this is our last example, which has several parts. Population decline. So exponential, but with a negative exponent. Exponential with a negative exponent. You might recall that this looks like, this is a decreasing function. So if I just draw a quick little sketch down here, starts at p sub 0. So right here could be our p sub 0. And then it's decreasing. So it's going down like this. Right? And that's what's going on here. Notice as this gets bigger and bigger, this is going to approach 0. So it's asymptotic to the x-axis. It is getting closer and closer to this x-axis, but never quite getting there. So this is what this decreasing function, a decline or a decay. We're declining, so this is what they call a decay function. So here we're actually having population decline as a Midwestern city's residents moves to the suburbs. And this is the function modeling the decline. And they're going to say, assume at time t equals 0, which p of 0, this is the initial population. They're telling us assume it's 1,000,000. So if it's 1,000,000, then we replace the p of 0 with 1,000,000, and p of t is 1,000,000 times e to the negative 0.04 t. Let's find the population at t equals 1 to the nearest 1,000. So for t equals 1, we have 1,000,000 times e to the power, so exponential, to the power negative 0.04 times 1 is just t, but I'll go ahead and do the times 1. All right, so after 1 year, the population goes from 1,000,000 to 960,789. Now they want this to the nearest 1,000, so 961,000. So 961,000. How long to the nearest tenth of a year will it take for the population to decline to 750,000? So this time they're giving us the P of t. P of t equals 750,000. So that's what we want to work with now. So 750,000 space equals the 1,000,000 times, I'm just going to copy this, all right? So what's the first thing we're going to do? We want to isolate the exponential, so divide through by the 1,000,000. So divide by 1,000,000. Remember, when I say this, we're doing it to both sides, of course. Whatever happens here is happening to both sides. So the 750,000 divided by 1,000,000, All right, leaves us with our exponential. We want to get to the exponent, so we need to get rid of the base e, and to do that, we use the inverse function natural log. So we'll take the natural log of both sides, of course, but I like to emphasize this because it's easy to forget. Open this a little bit, need a little bit wider. All right, so equals the natural log of 0.75, right? And that then equals the natural log of this exponential, but we know the natural log and the e cancel out. So we're just left with negative 0.04t. And now to solve for t, all we need to do is divide by the negative 0.04. Let's see, I'll write that here. So divide by negative 0.04. And here is t. So how long to nearest tenth of a year? So we're looking at 7.2 years. So in 7.2 years, the population will have decreased to 750,000, which notice is 3/4 of the original population. Okay, so that's 3/4 of the original population in 7.2 years. How long till half the original? Let me delete this. Let's do this again. How long to the nearest tenth of a year will it take for the population to half its initial number? Well, half its initial number, if it started at 1 million, half is 500,000 equals 1 million times e to the negative 0.04t. We divide both sides by 1 million, and since we're now at half the original population, we know it's going to be 1/2, right? Equals this divided by 1 million, right? 1/2, 0.5. Equals the exponential. Take the natural log of both sides. So the first thing we did was divide by 1 million. Now we're going to take the natural log of both sides. I'm just going to write take the natural log. So here we have ln of the 0.5, and that equals ln of all this. But since the natural log and e cancel out, we just have the negative 0.04t. So now all we have to do is divide by negative 0.04, and that would be 17.3 years. All right. I already drew you a brief sketch of what this looks like, so we already discussed its properties. All right, I hope that was useful in helping you solve some logarithmic and exponential equations and applications. Thank you for watching.